Hello everyone. So this is a question from JEE Mains 2026 6th April Shift 2. Given below are two statements. Statement 1, F2O less than H2O less than Cl2O is the correct trend in terms of bond angle. Statement 2, SiF4, SnF4 and PbF4 are ionic in nature. Okay, so we have to determine which one is true, which one is false. The chapters involved is P block, 12th, 11th and chemical bonding. Okay, so if we look at F2O and H2O, obviously both will have two lone pairs on oxygen. The bond angle in F2O is 103 degrees and the bond angle in H2O is 104.5 degree. Okay, so the observation is bond angle in H2O is greater than bond angle in F2O. Okay, so this is because of the greater electronegativity of fluorine than oxygen. Okay, this is due to greater electronegativity of fluorine than oxygen. Fluorine has a value of electronegativity 4, O has value of 3.5. Okay, so because of a very high electronegativity of fluorine, the bond pairs in OF2, that is these electrons, lie near to the fluorine atom. So these guys are more towards the fluorine atom. The electron density is more towards fluorine. Okay, so I will represent that by these dots. Okay, and therefore since they are far away towards fluorine, so therefore there is less repulsion and a smaller angle. Okay, in F2O. So because of this, in F2O we have less repulsion and a smaller angle. Cool. And compared to H2O, in H2O, the electrons will lie near to oxygen because oxygen has more electronegativity. So therefore, these electrons are actually near oxygen. So the electron density is very high near oxygen. So I will show that by using dots. Okay. So you can see these electrons lie very near to the oxygen atom. So therefore, there will be more repulsions among them. Okay. And therefore, there is a greater angle. So in the case of H2O, more repulsion and a greater angle. Okay, so on the basis of this, you might be expecting that bond angle in Cl2O to lie in between 104.5 degree and 103 degree. That is, to be specific, less than 104.5 and more than 103 degree. Okay, this is because the electronegativity of chlorine is 3 and it is smaller than fluorine, which is 4, but it is more than hydrogen, which is 2.2. Okay, so if we look at the structures OCl, OFF, OHH. Okay, so the electrons are near fluorine. Here they are very very near oxygen. Here, so here they will be somewhere here. Okay, so we expect that the maximum bond angle is in H2O, maximum repulsions. Then we expect the maximum bond angle here because the electrons are somewhere midway, and we expect the least angle here because they are extremely towards fluorine, so there will be least repulsions here. Okay, so the expected order should be F2O less than Cl2O less than H2O. Okay, but to our surprise, the actual order is F2O H2O and Cl2O. Cl2O has the maximum bond angle value. Okay, so there are three reasons for this observation. Okay, if we look at the structure of Cl2O, we have oxygen, chlorine, chlorine. Obviously, there are two lone pairs on oxygen. Okay, so the first reason is chlorine is present in the third period. Okay, and it is much larger than hydrogen, which is present in the first period, obviously, and also fluorine, which is present in the second period. Okay, so it is a bigger atom in size. So therefore in OCl2, that is this guy, the bulky chlorine atom, so this is a bigger atom, so these bulky atoms, they repel each other. Okay, and because of this repulsion, they push each other apart, and because of that there is an increase in the bond angle, and this angle is 111 degree to be specific. Okay, the second reason is, so let's write the configuration of every atom involved. Hydrogen, it is 1s1. Oxygen is 1s2, 2s2, 2px2, 2py1, 2pz1. For fluorine, it is 1s2, 2s2, 2px2, 2py2, 2pz1. And for chlorine, it is 1s2, 2s2, 2p6, 3s2, 3px2, 3py2, 3pz1, and also 3d0. Very important. Okay, putting a star mark here. So chlorine clearly belongs to the third period. So therefore it has vacant 3d orbitals. Okay, which is not in the case of fluorine or hydrogen. So here we don't have any vacant orbitals. Okay, so therefore the lone pair on the central oxygen atom, so in the case of chlorine, Cl2O, so we have these lone pairs here. So the lone pairs on the central, sorry, I drew the wrong diagram. So here we will have oxygen and fluorine. Yeah. So what I was saying is the lone pair on the central oxygen atom can delocalize into the 3d orbitals of, again, sorry, it should be chlorine. Yeah. So the point is that the lone pair on central oxygen atom can delocalize into the vacant 3d orbitals of chlorine. Okay, so which is known as back bonding. So with respect to diagram, I can show back bonding. So chlorine will have vacant or empty 3d orbitals, so I will draw them in this fashion. And obviously oxygen, the central oxygen, has filled 2p orbital carrying the lone pairs. So this is the 2p orbitals of oxygen having the lone pairs. So these guys, that is the empty 3d orbital of chlorine and the filled 2p orbital of oxygen, they can overlap, okay, resulting in a new bond. So that can be represented like this: chlorine and oxygen has this pair and this pair. Okay, so can you say there is some amount of overlap? So this is known as the d pi e pi bond. Okay, so because of the sharing of lone pairs of the sharing of lone pairs on oxygen, these lone pairs with the empty 3d orbitals of chlorine, okay, it gives the OCl bonds, it is this particular bond, partial double bond character, because they are being shared. This is also being shared. So these two bonds have some partial double bond character. Okay, and because of this, the electron density in these bonds are increasing. Okay, and because of that, there is more repulsion. This increase, this leads to an increase in the bond pair repulsions. So since there is a lot of electron density here, so these guys will even repel more. So because of this, this is one more reason why the bond angle increases to 111 degree. Okay, so I can draw that. So we'll have oxygen with lone pairs, chlorine, chlorine. So these guys are actually, shared with the empty d orbitals of chlorine, resulting in an increase in electron density and more repulsions. Okay, so This is the second reason. And the third reason is, now if you see the oxygen lone pairs, so this is these lone pairs are partially being used for back bonding. They are being shared with the d orbitals, empty d orbitals of chlorine, right? And since they are being shared, you can see the lone pair repulsion, that is these lone pair repulsions, it decreases because they are being shared now. Okay, and because of the decrease in these lone pair repulsions, these guys can, widen up. Okay, and therefore this is one more reason why there is, a very big unexpected increase in bond angle in the case of Cl2O. Okay, so the third reason is that since oxygen lone pairs are used for back bonding, lone pair repulsion decreases, allowing bond angle to widen or increase. Okay, so therefore because of these three reasons, statement 1, that is, the bond angle order is F2O less than H2O less than Cl2O. So this is a correct statement. Okay, now coming to the second statement. Second statement says that SiF4, SnF4 and PbF4 are, ionic. All three of them are ionic in nature. And one thing to know is that no bond is 100% or purely ionic or 100% or purely covalent. Okay, so they have some ionic percentage and some covalent percentage depending upon which we say that it is predominantly ionic or predominantly covalent. Okay, so we know that if the electronegativity difference between the two atoms is huge, then they result into a predominantly ionic bond. And if the electronegativity difference is less, or they are comparable, the electronegativity is comparable, then it results into a predominantly covalent bond. Okay, but the case is that silicon, tin and lead, these guys have very close electronegativity values. That is, silicon is 1.8 approximately, tin is 1.8 approximately, and lead is 1.9 approximately. Okay, so therefore we have to refer to Fajan's rules, since the anion F minus is same in all three of them. Okay, as we have to compare SiF4, SnF4 and PbF4, and all three of them have the same anion F minus. Okay, or the fluoride ion. Okay, according to Fajan's rules, smaller the cation, greater is its polarizing power. Very important. Smaller is the cation, greater is its polarizing power. Okay, the meaning of polarizing power is the ability of the cation to distort the cloud or the electron cloud of anion towards itself. Okay, very important. Polarizing power means ability of cation to distort electron cloud of anion towards itself. Okay, so with respect to diagram, so let's say that we have the cation, which is obviously smaller than the anion, and let's say they are as separate charges. So therefore in this scenario it is predominantly ionic. Okay, but because of the polarization produced by the cation, that is this guy, the electron cloud of the anion gets distorted. This is what is known as polarization. Okay, and because of the polarization, what happens is their electron clouds um, overlap. Okay, so this will lead into an increase in covalent character. So you can see now it is covalent. So therefore, more is the polarization, more is the covalent character. Okay. More is the polarization produced by the cation. Obviously, more is the covalent character of the bond. Okay. So in our case, the cations are Si plus 4. So this guy has, radius 40 picometer. It's the smallest. Then we have tin plus 4. Its size is 69 picometer. And then we have, lead plus 4, whose size is 78 picometer. So you can see Si plus 4 is the smallest. So it will produce the maximum polarization, because according to Fajan's rule, smaller is the cation, greater is its polarizing power. So this guy will produce the maximum polarizing power of, maximum polarization of fluoride anion, due to which it is predominantly covalent. Okay. And these two guys, that is SnF4 and PbF4, are predominantly ionic because, you know, the polarization produced by Sn plus 4 and Pb plus 4 is, comparatively less because of their bigger sizes. Okay. So therefore, statement 2, which says that SiF4, SnF4, PbF4 are ionic. So this is not a correct statement, because SiF4 is predominantly covalent and these two are, ionic. Okay. So therefore, statement 1 is true and statement 2 is false. Okay. Thank you.